there's a lot of lenses.
Okay, so that's
Okay, we ready?
Yeah, I think so.
yes.
Okay. I'm probably going to be giving the least technical talk today. It's a hard act to follow what you've seen so far. But what I'm going to talk about is building Windows 64-bit device drivers with fasm, which was an interesting proposition, and I'll talk about that a little bit later. And as an example of that, we'll show a hypervisor that Vid really wrote for the most part. I had gotten parts of it started, but Vid really helped me finish it up. And Vid's going to help me with this presentation, so just as I needed help with my code, I'll have Vid help me with the presentation as well. So our the goal for the project was to build something interesting, something that would be interesting to build and be a worthy project, and I picked the hypervisor to do that. I developed it in a 64-bit Windows device driver using fasm and the C language, C programming language. The reason that I put it in a device driver is because a lot of the hypervisor setup code requires access to ring 0.
Can you just define a hypervisor?
There's an answer.
Thank you.
That was a great segue, Tom. So, a hypervisor is a very thin layer of system software that sits directly on top of the hardware, abstracts the hardware, and allows you to launch virtual machines. For the most part, the industry interest in hypervisors is for multiple operating systems like VMware, Zen. Their big interest is in being able to run a number of operating systems concurrently. I have some different ideas for the use of a hypervisor that I'll talk a little bit about later. So pictures are worth 1,000 words, and this is a rather busy picture, and this is what Microsoft's vision for their Windows Server 2008, the hypervisor they're building. But forgetting a bunch of this crap that they're doing here, I just want you to focus on the fact that the hypervisor is this thin layer that sits directly on top of the real hardware, abstracts it, and provides a copy or a version of that hardware or any hardware that you want to define in software in hypervisor and run it concurrently. So it's this piece that we're focusing on.
That's a question from Hypervista. He
Yes.
asks, could we make a hypervisor?
Meaning, can you hypervise a hypervisor,
Yeah,
one on top of the other?
Like later.
Yeah, absolutely, it's possible. It's difficult if you're trying to hide the fact that you're using a hypervisor. Then you have to really get into some very tricky things in hiding hypervisor. But certainly you can, as long as your resources hold up, you can hypervise a hypervisor. And it has been done, actually. So the tools, of course, that I use are fasm. You know, what else? You'll need a favorite editor or IDE. I happen to use Visual Studio, but you can use any IDE. You're not going to use the compiler in Visual Studio. Of course, when you're doing driver work, you'll use the DDK, the Windows DDK, and then you'll need Windows Debug to see how things are going for you. Some really nice utilities that you can use in driver development. You can log on and for free get this utility from OSR. They specialize in device driver, Windows device drivers. You have to sign up and join, but once you do that, you can get these tools The neat thing about this OS driver utility is that a lot of times, at least for me, when I was developing this driver, I would like totally hammer my machine and would wipe out the registry, and I'd have to reload all the registry settings to get my driver loaded again so I could begin testing again. Well, the cool thing about this is you don't have to worry about that so much because it's got a nice little window, and we'll show it on how to launch your driver from an application, load it and run it.
You need to flush the disk cache before you load your driver.
Yes. Well, in some cases, it was actually deleting the driver entry in the registry.
Yeah.
And so it's a pain to have to go in and do regedit each time you do that. And so this tool here helps you get around that problem. And then sysinternals has what's called a debug view. Of course, Microsoft bought sysinternals last year. You can go there and get this debug view, and you can actually see your debug print messages on the machine that you're running the driver on. So you don't need to do a remote debugging. But later on in the talk, I'm going to show, Vid and I are going to show how to do remote debugging, which is really better, actually. But for something quick and dirty to see your debug messages, this utility from sysinternals is quite good. All right, the Windows device driver development. Again, these resources, again, I can't recommend OSR Online more. It's a great resource for Windows driver development. And here at Microsoft, at this URL, you can get your DDKs and the WinDebug. The books that I use heavily, and there are others out there, but I really, really like these, and they come in handy, particularly this one by Decker and Newcomer, Developing Windows NT Device Drivers. This one's also quite good. It's old, but it's back in reprint. In fact, OSR Online is now printing that one. And then, of course, the Solomon and Rusinovich's Windows Internals book. It's quite good. And I like this picture on this. This is an old picture of some circus act. This guy standing up on his motorcycle, driving it, while his buddy's standing on his back backwards, and he's getting ready to do a handstand.
So this is how the kernel works?
No, that's
how you feel sometimes.
That's how you feel, exactly. It's exactly how you feel most times when you're writing Windows device drivers. It feels very much like that. So some of the considerations. Inline assembly is absolutely not supported in 64-bit device drivers. You can certainly do it in 32-bit device drivers, but if you're thinking about porting your device drivers eventually to 64-bit, you should take all that assembly out and compile them to object files separately and then link them in with the DDK later. C++ is not a good idea for drivers in general, not just 64-bit. There's some argument about that, but I think it's a bad idea to use C++ in device drivers.
If you do it with consideration, it can be okay, but you need to be very careful about which features you use. You shouldn't use C++ exception handling.
Right, the exception handling is one of the real problems
it's
for
done
that.
a completely different way in the kernel when you use it.
Right, and some of the object-oriented stuff is a problem. The new DDK, which I haven't used and I'm not using in this project, is object-oriented by design, but anyway, as a general rule, C++ is not a good idea in device drivers. In running and testing your device drivers, 64-bit in particular for Windows XP 64-bit and Windows Vista 64-bit, the drivers just absolutely won't load. It's a security feature unless one of two things, actually one of three things are in place. A debugger is attached, which is nice that they provided that. So if you're running a debugger, you're in the development phase, and when it knows that, it will allow you to load that driver and run it. Or on boot up, if you push F8 and you get the standard screen to go into safe mode and all the other options. In these versions of the OS, there's an option in there that says disable driver signing, and you can do it that way too. And of course, the third way is to send your device driver off to Microsoft and have them sign it. But when you're developing it, it doesn't make a lot of sense. One other thing that we ran into, took about a day or so to figure out, that in these 64-bit versions of these OSs, you can't use debug print. You have to use debug print EX, which has this very long, I think three parameters. 4 parameters?
I'm not sure about.
Yeah, it probably is 4 parameters. But anyway, it costs us several days, so hopefully you won't do the same thing. And my apologies if I'm telling everybody stuff they already know, but basic structure of a device driver and your prologue, of course, NT DDK header file is included. You define your NT device name, and it's Unicode. The L, of course, means Unicode. The blah blah is what your device driver name is going to be. You have to set up the DOS device name, and then you declare your function headers. After that, you have your driver entry routine. This is when the driver starts. You instantiate the driver, and it begins to run. You create symbolic links to these devices that you've created. In our example, what we've done is we have all of our fasm demo functions in driver entry. In production, it's probably best to have it in a on-device call so that you can have an application turn on or off your functionality as you need it. But we put it in the driver entry because we want it to happen as soon as we load our driver. And so, again, going back to the basic device driver, you have your open functions after driver entry, and really this is where you would normally put most of your code that you want to have, some of your custom code. And then functions that close, and then a function that unloads the driver and cleans up all the resources. I think I'm going to skip over going over the driver source code for lack of time. Yeah. Okay, coding the hypervisor in fasm. This was quite an interesting journey, particularly in the beginning when I was trying to write it myself. I had some questions about how do I get the object files compiled properly with the DDK. So I wrote off to Microsoft, and the answer I got back twice was, why are you doing this with unsupported tools, meaning fasm? They actually want you to use the MASM compilers that are part of the DDK. So I went back
I thought they stopped supporting MASM about 10 years ago.
No, it's included in the DDK.
They don't sell it as a separate product anymore, but it's included with Visual
Yeah,
Studio.
but they haven't
DDK.
changed it in 10 years.
Yeah, they have.
Yeah, they have.
You know, Kip Irvine, when he puts his book out, he has MASM 6 or 5.5 or 6.5,
That's
whatever.
because you can't buy MASM separately anymore. You can
Yeah,
only get it with Visual
This
Studio.
is the DDK.
or
We're talking
DDK.
about the assemblers in the DDK. It's still MASM, but that's where they're doing their upgrading.
So you mean it is upgraded, it is maintained?
Oh yeah, they're maintaining it. In fact, he goes on, in his second post to me, he goes on to explain this. Again, he says very clearly to me, give up on non-supported tools, meaning fasm. All three of these assemblers come with the DDK. And he explains that with the bad press that Microsoft has been receiving on the instability of Windows, the drivers group finally got enough influence to get a version of the compiler they could release with the DDK that they knew would work. And so they really are trying to force you to use only their tools. But once we got through a few of the hurdles, fasm works beautifully in the device driver. Let me talk a little bit about the Intel support for virtualization. Of course, AMD has a similar support in their processors, but we're focusing on the Intel version. So with Intel's version, which they call VMX, the processor really will operate in two different modes. The VMX root mode, which is full privilege ring 0, and VMX non-root, which is the less privileged ring 0. So you can think of these as actually the hypervisor itself, or the VMM, the virtual machine monitor, and this mode is the virtual machine. And so the hypervisor will launch these into non-root mode. And so there's a number of events that will cause a virtual machine or this VMX non-root to exit back to the hypervisor. For performance, you want to minimize that, but sometimes you want the hypervisor to handle certain pieces of code or certain events. The ones that are built in that always cause an exit or a trap to the hypervisor is IO device access, specific instructions like CPU ID, access to certain control registers will always cause an exit. Calling a VM call will bump you out of the virtual machine and back down into the hypervisor. And when that happens, the states get swapped out of running. Only one's running at a time. So when you swap, if you're in a VM and you get a call out to the hypervisor, the state is saved, swapped out, and the hypervisor state, which was saved the last time it exited, gets instantiated, and they switch back and forth like that. And it's amazing, actually, that all this functionality is provided with just the inclusion of 10 more instructions in the CPU. I mentioned a while ago that the state of the various machines, the VMM or the hypervisor, gets swapped in and out. This state is saved in this very, very large and rather complex structure called a virtual machine control structure. And you'll see some of this, and this is, did really work very hard to get these populated properly. And he can talk a little bit about some of the problems and issues that we faced. But all the control registers get saved there. The debug registers, which Brno talked about, get saved off. All of these, instruction pointers, the stack pointers, the flags, the selectors, their base and limits, the access rights for the segments, all of that has to be populated into the VMCS to launch a virtual machine and the MSRs as well. And when you see this, you can understand why you need ring 0 to set all this up. There's a lot of stuff going on there that you need ring 0 for. So these are the 10 instructions. Some of them are pretty self-explanatory. VMX on or off will enable or disable the VMX operation on the box. A VM clear is really not, it's sort of counterintuitive, but you use VM clear to instantiate a new VMCS before you launch it, before you call it. And once you do that, once you call clear, then you load it, and then you can launch it with a VM call. VM launch. Right. Oh no, what I was thinking of, VMX on is one of the calls that you have to do last. And then VM launch. So those are the 10 instructions. So again, this is almost redundant, but before you can set it up, you have to, some of the basic things that you do as a programmer, you make sure that the processor that you're talking to, one is an Intel, and then it supports VMX, and there are a number of checks that you have to go through, some bits you have to check and or set in control register 4. You have to allocate a 4 kilobyte page aligned memory for your VMCS. You have to initialize it both for the guest and the host, the hypervisor and the virtual machine. And then you have to enable it. I'll skip over the source code review. So linking and building. Vid, I'm going to ask you to talk about this, because these are your
Okay.
build and link routines.
Okay, so This was actually my fast and easy way to make it. I only wrote my custom batch file. Actually, this file is not that interesting. Just set path to Windows DDK directory. Then it contains multiple compilers, so you just set path to directory which contains the compiler version that you use. In our case it is AMD64. Then we set directory to proper, then we set this environment variable to a directory with proper library files. And these are few object files that we always include. Now what would interest us more is this build C that don't you have it?
What's that?
This batch. You have it there? Build C.
Yes, it's on that machine. Oh, no, I have it on the other machine.
Don't you have it here? You don't have it here.
Frino,
This machine.
Frino, you can open that one too.
Okay, so for now I can describe C component arguments because they are in this batch file, which we don't have currently. At least I can explain linking parameters. So we link, first we list these object files, which we always need. Then we decide name of resulting file. We also produce system symbols file, program database or map file, so we can easier navigate this assembly. Drivers must be aligned at 80 hex. These are default values that Microsoft also uses for stack, so we does too. Subsystem has to be set to native. Drive, this is another switch which is needed to let the linker know this is a driver. Entry point is inside this library which does exception handling. No default library is needed, and that's all for the linker.
Next slide, build fasm.
And this is building fasm. Not much in here regarding this is fasm, which doesn't take command line arguments mostly, so nothing very interesting here. And build C. This is how we compile each C file. So compiler, source file. This is name of source file. This is name of destination object file. So we also produce assembly listing for the object file. It's in nesting syntax, but it helps us to see what exactly the compiler did. This is switch which I think enables generating this. I don't recall what is this. This is maximum warning level, and every warning causes is treated as error, so there are no warnings allowed. We don't want exception handling in our own objects because that we are sometimes in state where we cannot rely on system in anything. This switch generally does by default. This compiler also tries to link, and this switch tells it not to link. This is list of includes we use. These two, and these are two symbols you have to define when computing. That's all to the computing. Okay. Nothing for me? No.
And so kernel debugging. We selected 1394 FireWire for a number of reasons. One, it's off-the-shelf technology. It's available. It's on most of the modern machines these days, although I understand it's going away, maybe in 3 to 5 years.
Hasn't it been replaced by USB 2?
I think you have to mention why we're using FireWire. Because of WinDBG to debug kernel you have to have two computers.
Right. Yeah, I thought that was maybe understood. Maybe I do need to explain that. It's best to really do remote debugging when you're doing kernel debugging, because a lot of times, as I said earlier, you can really hose up your machine, which I've had, and it's hard. You don't want to really be debugging on your development machine, because your development environment could get destroyed, files could get misplaced or damaged, and so it's really best to run your test drivers on a remote machine that you don't really care about so much, and then do your debugging on a separate machine. And I do my debugging on my development machine, and I just have a target machine that all I do on that is just run these, and my kids use it to surf the internet. Another advantage of using it is that minimal code running on your target system. And this is a very cool aspect too of FireWire. It has direct access to the memory on the machine. And the client handles all the asynchronous calls and data transfers. And another really good reason too to use FireWire is it's really fast. It says here some of the statistics: a full system memory dump, about 128 megabits, would take over 3 hours on a serial bus, but with FireWire, it happens in about 15 seconds to dump the entire memory. So to set up your target machine, what you have to do is set it up to basically dual boot, so that you can boot into debug mode if you need to, or when you want to do that. And so the steps, of course, you have to open up a command window, and to get to the boot INI file, you have to turn off the hidden attribute so you can get to it and edit it. And then you have to add this line down here, the /debug port equals, and in this case, because we're using FireWire, it's 1394, and then you have to set up a channel. I use channel 10, but you can use any channel, I think, from 1 to 99. Then you have to reboot your machine. Now, in Windows Vista, it's a little bit different. They don't have a boot INI. There's another mechanism that they use, and I didn't talk about it here, but when I puts these slides up for download, I'll include the instructions on how to do it for Windows Vista. An additional tips that you want to do on your target machine is to disable the 1394, the FireWire controller in the device manager. And what that does for you is it improves the reliability of the debug. The downside is loss of some power management, but who cares? It's just your target machine. You're not doing much on it anyway. And you got to make sure it's the host controller and not the adapter, because you're going to need the adapter. So on the host machine, or the machine that you're going to use to do the remote debugging from, to set that up, of course, you have to install the WinDebug. And when you do that, the first time you install it, and I have a couple slides on, the first time you try to run it, it loads 2 separate drivers. And so to do that, to run WinDebug, you have to make these calls, and obviously it's easy to just put this in a batch file so you don't have to do all this typing. But you have to, in the command line, set up these commands.